Welcome back. Let us now see what are the daylight requirements in ECBC 2017. Above grade floor areas shall meet or exceed the useful daylight illuminance or UDI area requirements as listed in table 4.1 for 90% of the potential daylight time in a year. Percentage of the floor area varies with the level of ECBC compliance that a project wants to show. So as per this table, for business and educational buildings, 40% of the area should meet or exceed the UDI requirements for 90% of the potential daylight time in a year. For ECBC plus, it is 50%, and for ECBC, Super ECBC, it is 60%. Likewise, for other building types, the percentages are defined. To show compliance, there are two methods, one which involves simulation and the other method which needs manual calculations. Let us look at the simulation method. For simulation, we need a software. Only BE approved software shall be used to demonstrate compliance through the daylight simulation method. Building shall achieve illuminance level between 100 lux and 2000 lux for a minimum percentage of the floor area as was given in table 4.1 that we just saw for at least 90% of the potential daylight time. Illuminance levels for all spaces enclosed by permanent internal partitions, opaque, translucent or transparent, with height greater than or equal to 2 meters from the finished floor shall be measured. Now let us look at the method. Measurements shall be taken at a work plane height of 0.8 meter above the finished floor. The period of analysis shall be fixed for 8 hours per day. These 8 hours can be any time between 8 AM IST and 5 PM IST. This will result into 2,920 hours in total for all building types except schools. For schools, one has to analyze for 7 hours per day, and these 7 hours can be any time between 7 AM to 3 PM IST. Available useful daylight across a space shall be measured based on point-by-point grid values. UDI shall be calculated for at least 1 point for each square meter of the floor area. Fenestration shall be modeled with actual visible light transmission as per the details provided in the material specification sheet. All surrounding natural or man-made daylight obstructions shall be modeled. If the distance between the facade of the building and the surrounding natural or man-made daylight obstruction is less than or equal to twice the height of the man-made or natural sunlight obstructors. If the reflectance of the surface is not known, default reflectance of 30% or 0% shall be used for all vertical surfaces of man-made and natural obstructors respectively. Interior surface reflectance shall be modeled based on the actual material specification. If material specification is not available, default values are given in table 4.2 and they have to be used. Here are the default values for surface reflectances. For wall or vertical internal surfaces 50%, ceiling 70%, floor 20% and permanent furniture 50%. Now let us look at the daylight simulation method. We take an example. Suppose our building is located in Hyderabad and it has one block. Total built up area is 100 square meter. Assume the building is 10 meter by 10 meter and one floor. Floor to floor height is 3 meter. Window wall ratio 30%. Window visible light transmittance 0.41. Occupancy type day type office. Overhang and fins depth 1 meter. We model this in any software which is approved by BEE. In this case, we have used Design Builder. You can see the model. It's a square building and it has window which has both the overhang and the side fins. Once we model the building, then we set the UDI thresholds. We have set the lower illuminance threshold of 100 lux and the upper illuminance threshold of 2000 lux. We then simulate. In the simulation, we get UDI map as an output. Here you can see what areas meet the 90% requirement and which areas don't meet the 90% requirement. Interestingly, you will see that the areas which are closer to the window are not meeting the requirements. Why? Because they are getting overlit. For several hours in the year, they are getting more than 2000 lux, and therefore those hours are not considered as meeting the UDI requirement. After this map, we can get the actual UDI percentage area. We click the UDI percentage annual hours and set it to 90%. And here we can see more than 43% of the area is meeting the UDI requirements. Now let us look at manual daylighting compliance method. This method can be used for demonstrating compliance with daylighting requirements without any simulation. Daylight extent factors, or DEF, are mentioned in table 4.3, and they shall be used for manually calculating percentage of above grade floor area meeting the UDI requirement of 90% of the potential daylight time in a year. Here is the table. If you look at this table carefully, it has two columns for VLT less than 0.3 and VLT greater than or equal to 0.3. Then it has two major rows, one row for no shading or projection factor less than 0.4 and the another row for shading with projection factor greater than or equal to 0.4. If you look at the first row, we see that there are sub-rows, one for latitudes more than equal to 15 and another for latitude less than 15 degrees north. Then for all window type, we have the values for window when it is oriented towards north, south, east or west. Similarly, for the second row, which is with shading of projection factor greater than or equal to 0.4, there is no subdivision based on the latitudes. For all the latitudes it is applicable, but for different window types the values are different. Window types without light shelves, the values are given, and windows with light shelf, different values are given. So based on the location of the building, its latitude, based on the projection factor on the windows and the window types, whether they have light shelves or no light shelves, we can find out for different glass VLTs what would be the daylight extent factor. Now what do we do with this factor? Let us see how do we calculate the daylight area using this factor. In the direction perpendicular to the fenestration, multiply daylight extent factor by the head height of the fenestration, or till an opaque partition higher than the head height of the fenestration, whichever is less. In the direction parallel to the fenestration, daylight area extends a horizontal dimension equal to the width of the fenestration plus either 1 meter on each side of the aperture, or the distance to an opaque partition, or 1/2 the distance to an adjacent fenestration, whichever is less. For skylights, calculate the horizontal dimension in each direction equal to the top aperture dimension in that direction plus either the floor to ceiling height of the skylight or 1.5 times h for monitors, or h or 2h for sawtooth configuration, or distance to the nearest 1 meter or higher opaque partition, or 1/2 the distance to an adjacent skylight or vertical glazing, whichever is the least. A separate architectural plan shall be prepared with all daylight areas marked on the floor plan. A summary shall be provided showing compliance as per table 4.1. Glazed facades with non-cardinal orientations shall be categorized under a particular cardinal direction if its orientation is within plus minus 45 degrees of that cardinal direction. Any surrounding natural or man-made daylight obstructions shall not be considered in this method. Let us take an example. Suppose we have a building located in New Delhi with the floor area of 33 meters by 38 meters, that is a total 1254 square meter floor area. VLT of the glazing 0.39, assume all the glazings in all the orientation has the same VLT. External shading projection factor is more than or equal to 0.4. Light shelves are installed. Head height of fenestration is 3 meter. Then we look at the floor plan. You can see there are windows in the north, east, south and west. Windows in the north are numbered N1 to N8. In the east, E1 to E5, south S1 to S3 and west W1 to W4. Now what do? We find out the DEF. As given, the VLT is more than 0.3, therefore we take the corresponding column. We know that the shading is there in the building with projection factor greater than or equal to 0.4, so we take the second major row. There is a light shelf, so we take the row which has a light shelf related values. Then we get the DEF of 3.5 for north, 3.0 for south, 2.1 for east and 1.8 for the west facing windows. Once we get these values, then we can do this calculation. The calculation is very simple. First we take the windows which do not have opaque obstructions in front of them. Windows N7, N6 and N2 don't have opaque obstructions. Let us see the drawing again. So N6, N7 and N2 remaining windows have obstructions in front of them. So for these windows which do not have obstructions like N7, we take the fenestration width W as given in the drawing, 2 meters. We find out A, which is height into DEF. In this case it is 10.5. We find out B, which is L1 plus W plus L2. In this case we extend it both the sides by 1 meter. So the B becomes 2 plus 1 plus 1, which is 4. The area meeting the UDI requirements is equal to A into B is equal to 42 meter square. We find out for all the windows which do not have opaque obstructions. Those which have opaque obstructions, in this case we take a different calculation where A is distance till the parallel obstruction. And then again we find out the B and the areas. We sum total all these areas. We do this for the south facade, we do this for the east facade, and similarly we do it for the west facade. So we not only calculate, but we also mark these areas on the drawing, on the floor plan. Why do we do that? And why can't we just sum these areas? We can't do that. We simply cannot sum all these areas because some of these areas are overlapping. So if you see these orange areas, these two orange areas, these areas are being overlapping and they are counted twice. Let us take the area which is towards the window E5. This area is counted as daylit in the window S3 and it is also counted daylit in the window E5. Therefore, this area needs to be subtracted from the total area. Similarly, the area near window S1 and window W4 is being counted twice. It is counted in W4 as well as S1. Therefore, this also needs to be subtracted. So, we remove the overlapping areas by first adding the total overlapping areas and reducing it from the total daylight areas that we got from each orientation. So in this example, we are getting 616.5 meter square area which is meeting the daylight requirements of UDI 90% of the year. Now 616.5 is 49.2% of the total floor area, that is 1254 square meter. and this is more than 40% which is required by ECBC, and therefore this floor and this design meets the UDI requirements of ECBC 2015. Thank you.